chapter 1 complete. So we're going to move on and start talking about a different concept, but it still, in fact, ends up building on the stuff we've already been talking about. As I said back in the stuff in the previous chapter, the limit's kind of a foundational concept. In a typical classroom setting, I kind of go off on a bit of a tangent here, describing sort of the history of where calculus got developed. And it still kind of ends up, happening in the sense of describing sort of the different approaches people took that ended up giving us calculus back in the 17th century. Anyway, so it turned out calculus was developed by two folks, Sir Isaac Newton and Gottfried Wilhelm Leibniz, one in what we now call Germany, the other in England. Guess which one's which. And they were kind of working on different problems. Most of us probably recognize the name Sir Isaac Newton in connection with physics and gravity and apples falling and stuff like that. Leibniz may not be quite as well known if you're not already coming from a strong mathematical background or happen to be from a like a Germanic descent. But anyway, it turned out, largely speaking, they ended up coming up with calculus sort of from different directions. So like I said, we know of Newton as a physicist. Leibniz was kind of working on things from a more like geometrical standpoint. And as it turns out, the first two sections of chapter 2 in our text, as we transition into this new topic, end up presenting kind of these two different sides of the same coin, so to speak. We're actually going to start with the geometry perspective because I think it's a little easier to set up. So we're going to talk about what we call tangent lines to the graph of a function. So our function in this case, it looks like y equals square root of x. I'm just picking out as a particular example to work with. And where Leibniz was coming from was he was wanting to find lines tangent to some curve in space. So I don't want to delve into axes and things like that. We're still a little bit in flux at that stage. But anyway, we want to find a line tangent to the graph at a particular spot. So when I think of tangency, I'll often describe it, weirdly enough, in like basketball terms. It's kind of like a kiss off the glass, say. So let's pick out this particular point right here. So that's got an x coordinate of 4 and a y coordinate of 2. That's easy enough to check by plugging 4 into the formula I've given you right there. And we want to find a line tangent to our graph at that point. So he's going to kind of come across and just sort of graze the function at that spot. So the dotted line is maybe a little hard to pick up on my webcam display, but hopefully they've got the kind of traveling in that direction. Like I said, it's not really a true kiss off the glass for basketball fans out there, but hopefully you get the idea. Now, sure, I've drawn the tangent line, at least in a rough sense. Generally speaking, hopefully this doesn't come as a surprise to you. We probably don't just want to represent it with a picture. We want an equation that describes that line. Now, we've talked about this before. If you want an equation for a line, I've got to give you some information beforehand. We need a point on the line. That one's easy enough. He's right there. The trickier one is we need the slope. And normally, if I don't just straight up give you the slope, you'd expect me to give you like a second point so you can calculate the slope, right? That's sort of how these problems generally end up working out. That's the only point that we actually know this line passes through, given how we've defined tangency. So that's, kind of a problem, right? We've only got one point. Slope, requires 2 in general. So the big question ends up becoming, how can we get at the slope of this line if we don't have a second point on it? So this is where sort of the magic of calculus ends up originating. What if instead of demanding another point on the line, what if we approximate with a point that's close to the line? So given what we know about as you said, about our line, the only thing we really know is it should be traveling in the same direction as our kind of half parabola square root graph here. So why don't we try picking another point near the one we're interested in on the graph? So I'm going to pick this guy out right here. So that's technically 3 square root of 3, right? And if I try to draw that in, you'll see What I've constructed here is what you might call a secant line connecting these 2 points, and I could project it outward if I wanted to. And thanks to my poor artistic skills, that already looks like a pretty darn good approximation of the line that we've started with. So we've got 4, 2, and we've got 3 square root of 3. Now we have a line that's close in some sense, and that may already be setting off some bells in the memory banks, to the line we're interested in. Our slope should be close in some sense to the slope of our desired tangent line. Now I need some board space, but I like to, M for slope. That SEC is like a subscript for secant line. So we're trying to approximate here. Well, we have, change in y, so, I'll use, my y coordinate here minus that y coordinate there. So we have 2 over the square root of 3 divided by, let's see, 4 minus 3. And if you do some number crunching here, all right, so got my end result here. Moving a little closer. There you go. So when I worked this out, I have them reversed, but again, for slope calculation, so long as you keep stuff lined up, that's okay. We've got, looks like 2.267949. So, all right, so there's an approximate slope. Now, again, given the scale I put this graph at, you might end up thinking, well, that's probably good to go. It turns out you can actually do better. Because as it turns out, in the grand scheme of things, picking a point that's way over here as far as our target value was concerned, from 4 to 3, you could also have done from 4 to 5. You get a slightly different estimate. But that's not really close to our target point in the grand scheme of things. So instead, why don't we choose a point with an x coordinate closer to 4? So why not pick 3.5 instead of 3? Or why not pick 3.9? Now, back in the days of the invention of calculus, ready calculation tools weren't really there. So coming up with how to work out square roots of these things would have been kind of a bother. But you can see where this is going. Why do we pick right here? Well, we could get even closer. Now we can get even closer. It's just a matter of going into our calculator and adding like more nines to this thing as we go. And hopefully at this point it kind of stands to reason what we're doing. We're actually kind of just taking our target point, sliding it ever closer to 4. That sounds an awful lot like what we've spent all this time doing when it comes to calculating a limit. Now, I'm going to need to clear off a little space here, but before I do that, so what we're going to end up doing is picking out sort of like a target x value. And then we're going to look at this other point that we pick, instead of being, a different point of its own. We think of it as x plus or maybe minus a little bit. So I'm going to call this x plus h. So h is actually our parameter here. It's basically sort of like, how far off are we from the target value of x. So if that bothers you that x plus h is on this side, just remember, in this instance, h would be negative, which we're just adding something negative. Same thing as subtracting. All right, so now I need to clear off a little board space so we can try to investigate what's happening here. So bear with me. All right, so replacing 4 with x and looking at our other point as x plus h, like I said, a little bit off x. Our slope formula is going to look something like this. Our function, square root of x plus h minus the square root of x over x plus h minus x. And you're probably saying to yourself, well, x minus x, those guys go away. So we have square root of x plus h minus square root of x up top, and then all we have left down below is just h. Now, we want to keep sort of sliding that h value ever closer to the the target x coordinate. So now we're taking a limit. This is the limit. Now it can be a little tricky here because we've technically got two variables in play, but this is a limit as we let h go down to 0. You can phrase it in other ways, but for our purposes, this is going to end up working out the best. So x plus h minus square root of x over h. And so now we need to evaluate this limit. The good news is we just spent an entire chapter building up ways to deal with things like this. In this instance, hopefully this rings a bell, we need to rationalize the numerator of this thing. So x plus h plus square root of x multiplied by that up top. Whatever we do to the top, we got to do to the bottom. And now I need to free up a little space here, so I apologize for that. But so now, by design, since we've done this rationalization thing a bunch at this point, square of the first guy minus square of the second guy, that's just getting rid of our square root symbols. And then down below, we have h times this stuff. And again, if you wanted to build this up by starting with 4, you could do so. I'm just picking x as a sort of a stand-in if we wanted to do this at different points. So again, x minus x, they go poof. Now we have the limit. This h is running off towards 0. Shrink my 0 down so that's a bit clearer. Square root of x plus h plus square root of x. And lo and behold, these guys would now conveniently see each other out of the calculation. We have 1 over just this guy. So direct substitution would have failed us initially because plugging in h equals 0 just automatically tells us we've got a bad denominator. Here, though, we can plug in h equals 0 just fine. X plus 0. Yeah, that's a little pedantic to say the square root of x plus 0, but I want to make sure you see what's happening. All right. So, as it turns out, by having shifted this to using a general x instead of the specific 0.4, we've now used this limiting process to build up a formula for our tangent line slope that we can use for any x value for which our function was defined in the first place. So for any square root, we're able to work out a slope for that tangent line equation, and then in turn use that to build up, an equation for the tangent line. All right, so running short on time here, but yeah, this notion that we've seen, it may look a little familiar. There were a couple of homework problems that looked like this previously in terms of the overall format. We'll dig in our next video and take a look at exactly what this thing is like in math terms.